all, welcome to EC Electronics. So in this video we are going to see a DSP architecture. So we'll be discussing about the TMS320C5x DSP processor architecture. Okay, so we'll be seeing what are the various elements presented, what are the various units, and each of the elements in detail we'll be seeing, and also how to draw the entire architecture diagram we'll be seeing towards the end. Okay, and also for your reference, I've given the PDF of this DSP architecture in the description. So if you want to study in depth, you can have a look, and also the architecture diagram you can see in that PDF. Okay, so let us see the architecture of TMS320C5x DSP processor. So in today's video we are going to discuss about the architecture of TMS320C5x DSP, that is a digital signal processor. So this is a very commonly asked type of DSP processor. Okay, especially for DSP exams. So first we are going to see the most important features of this DSP. Then we'll be seeing the various areas like memory area, what all things are present in memory unit, what all things are present in CPU, what all things are the most important peripherals. These things we are going to see then, and later on or towards the end we'll be seeing how to draw the total figure. There is a total architecture structure we'll be seeing towards the end. Okay, so before all these things we are going to see the most important features. So this TMS320C5x DSP processor, it is a 5th generation DSP or digital signal processor from Texas Instruments. It is a 16-bit fixed point processors, that is it is having a CPU which is a central processing unit of 16-bit size. Okay, that is processing size is 16-bit. So it is a 16-bit CPU. Then third one, it is having advanced Harvard architecture. So they're generally based on the memory organization, you can classify the processor architectures are von Neumann and Harvard. So von Neumann is the architecture you see in all early processors where the instruction and the program memory are combined together. Whereas for Harvard architecture, both are organized as separate. Here it is an advanced Harvard, means it is having separate program and data memory. Okay, then fourth point is 50 million instructions per second. It can process 50 million instructions per second. 50 MIPS is the rate of processing of the TMS320C5x DSP. Then as I said, there are mainly 3 different areas. We'll be discussing about these 3 areas in detail. So just know that there are 3 different areas. Memory area is there, which consists of various memories. There is program memory, various data memories, all those things present in the memory area. Then there is a CPU, which is having all the important data processing registers and the processing units, ALUs and everything. We'll be seeing all this thing in detail. Then the peripherals. There are various peripherals also connected to this device. What all are the major peripherals also we will be seeing. Okay, so that are the 3 major areas. Then the instruction cycle, single instruction cycle is having timing of 20 to 50 nanoseconds. Okay, so that is the execution time of a single cycle. Then that is single cycle is having a duration of either 20 or up to 50 nanoseconds. Then the other important features are it is having a programmable timer and a PLL, and also IEEE standard JTAG ports are present. There is a DMA interface, and there are 2 different voltage operations, either 5 volt or 3 volt operation. For low power dissipation mode it is 5 volt, and for power down modes it is 3 volt. So it can have either 5 volt or 3 volt operations. So these are the most important features of this DSP processor or DSP. Next we are going to see about these 3 different areas. And as I said in the beginning, after studying these 3 areas, towards the end we'll be seeing the entire architecture, how to draw the entire architecture in detail. Okay. So next we are going to discuss about the memory organization of the TMS320C5x processor. Okay, so this is the on-chip memory of the processor, and Other than that, there is also external memory connection. Okay, so this much of blocks are present in the on-chip memory. And also you have to see that there is connection to the database and also to the program bus. Okay, so while drawing the last entire architecture, I'll be only drawing like a memory unit. There won't be the details. So when you are drawing your examination paper, you have to reproduce this block. Okay, not just the memory, but you have to draw these entire blocks. There are 4 blocks, you have to draw it, and also you have to mark the connections. There is connection to this program bus and there is a database. Okay, so let us see what all units are present in the memory area or in the memory structure. So the first block is program ROM. Okay, so you can call it as a PROM. So the PROM is having a size of 2K to 32K words. Okay, so as we have discussed in the beginning, the CPU is processing like words, or it is 16-bit CPU. So it will be processed. 16-bit means it is one word, right? So the CPU is actually processing words, and the size of this PROM can be from 2K to 32K words it can store. Okay, now what is the main purpose of this PROM or this program ROM? The first block is actually, it is used to permanently store the program code for a specific application during the manufacturing of the chip itself. Okay, so during the manufacturing of the chip itself, we are going to write this PROM memory. Okay, so the processor has an option of boot loading the content of the PROM to internal or external RAM during the power on reset. So you can load the contents of this RAM which was actually stored into it during the manufacturing time when the power on reset is happening. So when the processor is getting a reset, every time you can boot the memory or it can be loaded. Okay, that is, you can load the memory from the PROM on power on reset. Okay, so the content of the PROM can also be protected so that any external device cannot have access to the program code. So it is actually the program code and the external devices is not having access to this memory. Okay, so the main things is that this memory is a permanent memory. It is actually written during the time of manufacturing of the chip itself, and the processor will actually load the memory. This is whatever thing it is required. It will take at the time of power on reset or during the booting time, and the other external devices are prevented from accessing this memory. So that is all about the program ROM or PROM. Okay, also the size is from 2K to 32K. Next one is data/program SARAM. SARAM means it is single access RAM. Okay, so that is SARAM. I have written it here. SARAM is single access RAM, and the size is from 1K to 9K. It is actually depending on the various versions of this processor. So this processor itself is having various variations in its series, right? So on various variations, there will be, the size can vary from 1K to 9K. Anyway, the size of this SARAM ranges from 1K to 9K words. Okay, now this is a memory in which you can store either data memory or program memory or a combination of both. Okay, so that is all about the SARAM. It is single access RAM and it can store either data or program or can have a combination. Moving on to the third one, which is the DARAM, and these two blocks, actually there are 3 blocks. There is a block 0, block 1 and block 2. It is divided as 3 blocks, right? So these 3 blocks corresponds to DARAM. DARAM means it is dual access RAM, and there are 3 blocks of dual access RAM. There is a block 0, block 1 and block 2. So first let us discuss about the block 0. The block 0 is data/program DRAM. Means it can store either data or program. And the size is 512 into 16 bits. That is, it can store 512 words. Okay. So that is all about the block 0 DRAM. Then for block 1, the one in the bottom, it is a data DRAM, means it can store only data. Okay, and the size is 512 into 16 bits, means again 512 words it can store. The third DRAM block is block 2. It is again a data DRAM, means it can also store only data, and the size is 32 into 16, that is 32 words it can store. Okay, so that is all about the DRAM, and the total size of the DRAM is dual access RAM has a size of, it can store 1056 words. Totally, if you combine these 3 blocks, the size will be 1056 blocks. Okay. Sorry, 1056 words. Okay. So that is all about the memory organization in a chip. That is on chip. This much of memory elements are present. There is a program ROM. There is a SRAM. There is 3 blocks of DRAMs. Now moving on to the external memory. The external memory consists of program memory, data memory, and also external I/O address space. Now let us see the size details. 64K bar 16-bit means it can have 64K words of external program memory. Then 64K into 16, again 64K words of external data memory, and 64K words of external I/O address space. So these are the external memories which can be connected to this DSP architecture. Okay, and you connect the external buses here. There is a data bus. It is an external data bus. This is the external address bus. Okay, so that is all about the memory organization of the TMS320C5x processor. So the memory is organized as there is on-chip memory blocks and there is external memory which can be connected through external buses. So the on-chip memory is divided into the program memory and 2 types of data memories. It can be SRAM or DRAM. So the SRAM is having only 1 block and there is 3 blocks of, see here, 3 blocks of DRAMs. Okay. So that's all about the memory organization. Now let us see the CPU architecture. The next session of the processor that we are going to see is CPU. So CPU is the core of the processor. It will be doing all the major operations or processings. Okay. And all the important elements are actually present inside the CPU. So let us see about the CPU in detail, but yet in an exam point of view. Okay. So we'll start from this end. So the first structure is called program controller. This entire block is called program controller unit. And the function of the program controller, it contains all the elements that decodes the instructions and manages the CPU pipeline, stores the status of the CPU operation, and decodes the conditional operation. All these things we are doing with the help of the program controller. And so due to the parallelism in the architecture, the program controller can execute 3 concurrent instructions or simultaneous memory operations in a particular machine cycle. So in a machine cycle, it will be performing 3 concurrent instruction processing. Okay, so that is the brief about a program controller. And what all things are present in the program controller? There is a program counter, there is a status and control. These are actually registers. Status and control registers are there, hardware stack, address generation logic, and instruction register. Okay, so let us see about these things in detail. So the PC, we know that the first unit is a program counter. So just like in all processors, program counter will be containing the instruction to be executed next. The address of the instruction to be executed next will be stored in the program counter. It is a 16-bit program counter. Okay, that is the first element. The second element is status and control registers. Now let us see what are the status and control registers present. there is a 16-bit status registers. That is 16-bit status registers ST0 and ST1 is present. Okay, so what all things are present in this unit? There is ST0, ST1. So these are 16-bit status registers. Then there is processor mode status register, which is PMST. What is PMST? It is processor mode status register. Okay. Then next one is CBCR. CBCR means circular buffer control register. So these are the most important status and control registers present in this area. There is ST0 and ST1. These are simple status registers, and processor mode status register and circular buffer control register, which is CBCR. So these are the registers present in the second area. Okay. Moving on to the third area. The third area consists of the hardware stack, right? So the hardware stack is actually 16 by 16 bit. Means it has 16 words. It can store 16 words. Okay. So that is the size of a hardware stack. Okay. So that is the third element. Moving on to the fourth element, that is an address generation logic. So based on the instructions, it will be generating addresses. Okay. Then the last one is an instruction register. Just like any other processor, this instruction register will be storing the instructions. Okay. So that is the instruction register, and these are the units present in the program controller section. How many elements are there? 1, 2, 3, 4 and 5. And apart from this, there are interrupt flag registers and interrupt mask registers. Okay. So these are the main elements present in a program controller area. The next element present is memory mapped registers. So this memory mapped registers consist of various registers for CPU, serial port, timers and also wait state generators. Okay, so we'll see about the wait state generators later, but just know that it is again having some registers for controlling and coordinating purposes. Okay, and they are 16-bit registers. Okay, so that is all about the memory mapped registers. Okay, moving on to the next area, which is auxiliary register arithmetical unit. Auxiliary register arithmetic unit, ARAU. It consists of 8 16-bit auxiliary registers, AR0 to AR7. I have written it here. And along with that, there is a 3-bit auxiliary register pointer, ARP. Okay, I'll write it here. There is a ARP, which is a 3-bit pointer. Then there is a 16-bit index register represented as INDX. So this is 3-bit pointer. This is 16-bit index register. And there is a 16-bit auxiliary register compare register. Okay, so that is ARCR. Again, 16-bit. So this is a compare register, auxiliary register, compare register. Okay, so these are the 3 other elements present along with this AR0 to AR7. Okay, and also there is an unsigned 16-bit arithmetic unit, ARAU. Okay, ARAU, which is again a 16-bit unit. Now, so what are the other elements present along with this AR0 to AR7? So these are auxiliary registers. Along with it, there is a 3-bit pointer, 16-bit index register, 16-bit compare register, and an arithmetical unit. Okay. Now this ARAU, which is the last element we have discussed, is used to calculate the indirect address using the contents of ARP, INDX, and ARCR. Okay, so it is used for address calculation also, this ARAU. That is the arithmetical unit. Okay, so that is all about the elements present, and also that is the auxiliary register arithmetical unit. And this auxiliary registers can also be used as general purpose registers for holding the operands for arithmetical and logical unit operation. So there is an ALU here. So while doing the ALU operations, these registers, there is AR0 to AR7, these registers can be used as general purpose registers for holding the operands. Okay, so that is the auxiliary register area, which is consisting of the auxiliary registers, and also along with it there are some other elements also. We have discussed that what are the elements. Okay, now moving on to the next part of the CPU is CALU, which is Central Arithmetical and Logical Unit. Now the various elements present in the CALU is written inside. There is a multiplier, which is a 16 by 16 multiplier. Then there is a 32-bit accumulator. There is a 32-bit accumulator buffer. Then there are shifters and also ALU. Okay. And other than that, there is a 32-bit product register, which is represented as P. Yeah. So there is a product register represented as PREG, again a 32-bit one. And the shifters are, there is 0 to 16-bit left parallel shifter and 0 to 16-bit right parallel shifter. So these are actually parallel shifters, and 0 to 16-bit left and right shifters are present. Okay, now talking about the ALU can have two operands. One operand will be in the accumulator, one can be in the data memory or in the internal registers, or can be given as an immediate data. And after the ALU operation, the result will be stored in the 32-bit accumulator. Okay, so that is all about the ALU. Now moving on to the multiplier unit. The multiplier is a 16 by 16-bit multiplier, and it will be multiplying 2's complement data form, and the resultant will be 16 to 16 will be 32. The product will have a size of 32, and this result will be stored in the product register. Okay, so PREG is the product register, which is actually storing the result of this multiplier. Okay, so that is all about the multiplier unit. So these are the most important things you should be knowing in an exam point of view. If you go into the depth, there is a lot of things to learn, but if you want to study as an exam point of view, you should be knowing only this much of things. And also for your reference, I am going to give the link of the PDF in the description. Okay, if you want to have a thorough reading of the elements and the architecture, and the entire architecture is given. Okay, so that is all about the CLU. Moving on to the last element or the block present in the CPU, which is a parallel logic unit or PLU. So this is actually an additional unit. So this PLU will be performing logical operations without affecting the accumulator or the product register. Okay, so this will be working as a separate entity without affecting the accumulator and the product register. So the product register will be storing the multiplied result, and the accumulator will be storing the result of ALU, right? So the multiplier result is here and the ALU result is in the accumulator. Okay, so PLU, we are talking about this unit, right? So the PLU is working as a separate entity, and it is mainly concentrating on the Boolean operations or bit manipulations mainly. It can set, clear, test and or toggle the bits of status register, control register, or in the data memory locations. Okay, so in order to set or clear any bits, or in order to perform mainly bit manipulations, we use the parallel logic unit, and it is not affecting the product register or the accumulator. Okay, so these are the units present inside a CPU. I just want to brief up in 2-3 seconds. The first one we have discussed is a program controller. It is actually acting as a control entity. It is having all the controlling elements, the program counter, the status and the control register, address generation unit, instruction units, and other than there is interrupt, mask and registers. Okay, and moving on to the next part, there are two type of registers: memory mapped registers and auxiliary registers. Okay, so along with these auxiliary registers, there are certain other units also. We have explained about it, and the most important part, which is a core part actually, where the basic operations are actually happening in this unit, which consists of multiplier, accumulator buffer, shifter, parallel shifters, and ALU and product register. So the main operation, so the processing is actually happening in the central arithmetical and logical unit. Then the last one is the parallel logic unit, which will be actually performing some additional bit manipulations or setting and clearing of bits. Okay, so this is all about the elements present in a CPU. And also you should be noting down that there is connections towards the program bus. Sorry, there is connection from the program bus to the memory mapped register, to the CALU, and also to this TLU unit. And also here this is database. Okay, here you can see this is a database, and the database there is connections to the CALU and to this program controller. Why? Because towards the end, while drawing the entire architecture, I'll be only drawing as a CPU. Okay, in that you have to, so when I'm drawing CPU for your exam, you have to actually draw the entire block, which is this. And you have to also mark these arrows connected to the program bus and the database. That's why I've told you to note down the arrows also. Anyway, I'm sharing the PDF so that you can directly look it over the PDF. Okay. So that's all about the CPU. Now we are going to see about the peripherals and its details. So next we are going to discuss about the peripherals of this DSP processor. Before seeing into the peripherals drawn in this diagram, we'll be seeing some other elements also. So the first element, which is the most important one, we are going to see is a clock generator. So the clock generator, its purpose is to generate the clock signals for the processor, for the CPU. Okay. So it consists of an oscillator. There is an internal oscillator and a PLL. Okay. And this clock generator circuit is actually derived. It is actually derived, or it is driven with the help of an external crystal resonator. Okay. So this crystal resonator actually drives this clock generator, and it will be providing the sufficient frequency or the signals for this clock generator. And then the PLL, what it will be doing is, it will be multiplying this external signal or this external clock generated by the resonator by some factors, and it produces the desired clock for the input clock for the CPU. Okay. So this PLL will multiply the external clock with some prescaler factor or some multiplying with some factor and produce the desired clock, and it is given to the CPU. Okay. So that is the working of a clock generator. It actually generates the clock, and the PLL divides it with some factor and produces the desired clock, and it is given to the CPU. Okay. So that is all about the first element, which is a clock generator. Moving on to the second one, which is a serial port. So you can see there are serial port 1, serial port 2, TDM serial port, and buffered serial ports. Okay. So there are general purpose serial ports. These two are general purpose serial ports, and there is a special TDM serial port, and also there is a buffered serial port. Okay. So these are the first type of elements or the first type of peripherals present in the architecture, and these serial port can operate up to 1/4 of the machine cycle. Okay, and the serial communication data can be in either bytes or in words. So can be sending the data to the serial port. The size of the data can be either byte size or word size, and it can operate up to 1/4 speed or the frequency of machine cycle. Okay, so that's all about the serial port structure. Next is the timer, which is a very important peripheral for the unit. Okay, so the timer, there is a 16-bit hardware timer. Okay, and this 16-bit hardware timer, we'll write timer here. This is a 16-bit hardware timer and with a 4-bit prescaler. Okay. So the 16-bit timer is having a 4-bit prescaler also. Okay. And this programmable timer generates clock at a rate between 1/2 and 1/32 of the machine cycle rate. Okay, so this timer is actually generating the clocks in either 1/2 or in the range of 1/2 to 1/32 of the machine cycle. Okay, machine cycle. That is the clock period of the timer. Okay. So that is the most important parts of the timer. Now in the timer there are some control registers also. There is a timer control register TCR. The registers associated with this timer is timer control register TCR, then timer counter register TIM, that is timer counter register. Then there is timer period register PRD. Okay, so these are the three registers associated with this timer. Okay, the timer can be stopped, restarted, reset or disabled by specific status bits. So with the help of these registers, you can either start, stop, reset or disable the timer. So these are the three registers which can control and operate the timer. What are the three registers? Timer control register, timer counter register, then the timer period register. We can set the period, can either convert to counter, or we can have various control areas inside these registers. Okay, so these are the three registers associated with the timer. So if you brief up the timer, you can say it is a 16-bit timer with a 4-bit prescaler, and the machine cycle is, that is, its clock rate is, the timer clock rate is 1/2 to 1/32 in this range of the machine cycle. Then there are three main registers associated with it, and these registers can be used to start, stop, reset or delay the time. Okay, so that's all about the timer. Now moving on to the next one, which is actually not given in this diagram, but I have explained. Software programmable wait state generators and HPI, which is host port interface. Okay, so this software programmable wait state generator is actually not drawn here, but you should be knowing it. Okay, so why this software programmable wait state generators are used? So these are nothing but the wait state generators. Now when the processor or the DSP is in requirement of wait states, consider that the processor or the CPU, we are going to connect with some external elements. We are going to connect the DSP with some external elements, and we require some connections or some transactions between these external elements or some external memory, let's say. But this external device or memory which we are connecting is a slower one. Okay, slower than the speed of this DSP. So in that case, for the external entity to complete its execution and give the result, the processor has to undergo an idle period, okay, in order to get the result from the external entity. So in that case, there is a requirement of wait state. And this software programmable wait state generators help in creating of wait states or wait cycles. In that wait cycles, the processor will be actually waiting for the external entity to give the desired value or the data. Okay, so that is the next element. Then HPI is host port interface. Now consider that this DSP is going to be connected with some other host processor. So in order to have connections between the memory and the transactions between the host port or the host processor, so there is a connection between the DSP and a host processor. Consider that there is a big unit in which there is a host processor, and we are going to connect the DSP along with the host processor in that unit. So for the connections or the transactions between the host processor and the digital signal processor, we require a host port interface. Okay, so that is all about a HPI. So HPI used here is a 8-bit parallel IO port. Okay, so this port is 8-bit parallel IO port. It is used for transactions between the host processor and this DSP. Then last unit is test and emulation, used for some testing and emulation purpose. Okay, so that's all about the peripherals. Now we are going to see that how can we actually draw these three elements. That is, the memory element is there is a CPU and these peripheral units. How can we draw this together, or how can we integrate these elements together as a DSP architecture? Let us see. So this is the complete architecture of the DSP TMS320C5x processor. Okay, so it consists of the elements which we have explained in detail. The CPU is there, the memory and the peripherals. So this is how the entire architecture connects or integrates the three elements: the CPU, the memory and the peripherals. So we have explained about all these things. Only the left out was how to connect the elements. So I've tried to draw all the elements as much as possible, but the elements inside the CALU and some other things. Here I've only marked the abbreviations. The detailing, I've explained it already. So while drawing your examination paper, try to draw the detailed figure which we have already explained. Okay. So you have to write it: program counter, status and control register, hardware stack, address generation unit and instruction register. And there are also some other signals connected to this processor architecture, which is memory control signals, then system control signals, then interrupts, then there is DMA interface. There will be one port for DMA connection and DMA transaction. Okay, and also there is a clock. So we have already discussed about the clock generation unit, and it will be generating and divided by the PLL. The desired clock frequency will be given to the CPU. Okay, so these are the external signals connected, and there is program bus, there is a data bus. Okay, and also these elements are connected to the program and data bus. See, arrows are marked. Okay, so this is all about the entire architecture of the TMS320C5x processor. So the main elements are the program and the data memory, the memory units, program memory, SARAM, DRAM, 3 DRAM blocks. It consists of the memory unit or the memory area. Then there is a processor, and then there are various peripherals connected. Okay, all the peripherals are not drawn here, but mostly all the peripherals are drawn, and the other peripherals we have explained already. Okay, so you can write it down. You don't need to draw the other peripherals in this diagram. Okay, so that is all about the TMS320C5x processor architecture. So I'm really hoping that you understood the architecture. It is actually a theory topic. You just need to study what all elements are present and what are the working. That's all important while studying an architecture, right? Okay, so if you found the video useful, please to give it a thumbs up and also share it with your friends. And if you want more videos, please to subscribe to the channel. Thanks for watching and keep on watching.